Hello and welcome again to my course Applied Business Statistics. In the previous session, we talked about the sampling distributions of the some sample statistics, and we described in detail the idea behind sampling distribution. We talked about the philosophy of sampling distributions. We defined some terms which are necessary to understand the idea behind sampling distributions, like population, sample, parameter, and uh, sample statistics. So they are necessary to understand this idea. Then we have given some examples about the definition of sampling distribution itself. In this video, we are going to be more specific and talk about the sampling distribution of the mean and the sample proportion. We are talking about the sampling distribution of the sample mean, the sample mean, which we have call it X bar. X bar, the sample mean, we want to study here in detail or specific the sampling distribution of X bar. And later, we'll study the sampling distribution of the sample proportion. Now, to, to be more specific about the sampling distribution of any sample statistics, we have to define three things. First, the shape of the distribution. What distribution does it belong to? Right? That's the first one. The second one is the mean of this distribution, the average of this distribution. And the third, the variance or the standard error. We mentioned earlier in the previous session, we mentioned that the uh, the standard error is the square root of the variance, or the variance is the square root, the standard error squared. Standard error squared. So each sampling distribution is defined by three things: the shape, which is the distribution, and the mean and the variance. Three things, right? Specifically for the mean, the sampling distribution of the mean, the sample, we gave example and we show what is the shape of the sampling distribution of the mean. And we concluded by the end of the previous session that the sample distribution of sampling distribution of the mean, sample mean, looks like normal distributed, the bell shape, normal distribution with mean mu. The mean is the expected value or the expectation of the sample statistic itself, the expectation of X bar. What do you expect? The expectation equals the average of all averages. The average of all averages. We call it expectation or expected value of the of X bar. The average of all X bars. The average of all averages. That's the expectation, which we mentioned in the previous video, that the variance, the expected value or the average of averages equals the population mean, which is we call mu. So mu X bars, that means the expected value of X bar or the average of all averages equals the mu, which is the population mean. The population mean, right? The second thing is the standard error, which for X bar, which we called sigma X bar, equals the standard error of the population X itself, which equals sigma. The population standard deviation, sigma is the standard deviation of the population. So the standard error of X bar is the standard deviation of the population divided by the square root of n. N is the sample size, right? So this is the second thing. We said the first one, is the expected value of x bar is mu, and the second result is that the standard of x bar is the standard deviation of the population divided by the square root of n, the sample size. Right? This we call the standard error. That means that the variance of or the variance can be also called mean square error, which is the standard error square. We call it sometimes mean square error, or the variance. The variance of x bar is sigma squared. That means the variance of the population x itself divided by n. So that means like we square the whole value, sigma over square root of n, we make it squared, right? And we get the variance instead of standard error, right? So we have two things, mu x bar and sigma x bar, right? The third thing which finish the definition of the standard error is the shape of the distribution. To describe the shape more exact description of the shape of the distribution, we theoretically we say that if the population x, the original population from which we draw the sample itself, is the population x, is the original population from which we draw the sample, is normally distributed, then x bar is also normally distributed. It means it has the same shape, regardless of the sample size. Whatever the sample size, if it is 2 or 3 observations, even if the sample is only 2 or 3 units, and the population x from which we draw the sample is normally distributed, then x bar is normally distributed. That's one thing, right? That's definite result, exact result. And the other thing, but if the population x from which we draw the sample is not normally distributed, or we do not know the distribution of x, then we do not know whatever the sampling distribution or the distribution of x bar. We do not know it, but if we make n large enough, large does not necessarily to be very large, but at least 30 units, at least 30 observation. According to the central limit theorem, we have the same results. That if the sample size is large, at least 30 units, 30 observation, then x bar is approximately normal distribution. It becomes more and more similar to the normal distribution, the bell shape. Then that if it is very large, like n equals 500 or something like that, then it must be normally distributed. As the sample size get bigger, the distribution of x bar becomes more normal, more bell-shaped, right? Regardless of the shape of the population itself, whatever the distribution of x, right? Then we have two cases. In both cases, we have the x bar is normally distributed, right? The first case, if the population itself is normally distributed, there is no condition about the sample size. But if this x, the original population from which we draw the sample, is not normally distributed, then we must have a larger sample, and we use the same results according to the central limit theorem. Right, then we have, as a result, can summarize the result. Usually we have the sampling distribution of X bar, the sample mean, is normally distributed with mean mu and standard error sigma over square root of n. This is the final result. That's summing up all what we mentioned, right? That's the most important result which we get. Again, we say the sampling distribution of the mean, I mean the sample mean here, normally distributed with mean mu, this is the population mean, and the standard error equals sigma, which is the population standard deviation, over square root of n, which is the sample size, right? Only one condition: if the original population is not normal distributed, we have to have a larger sample size over 30 units, at least 30 units. That's the only condition we have. But if the population is normal distributed, then the sample could be small, no problem. That's the final results we get here. Final conclusion in which we get in this part of the. Now we have an example. Example two. We have example one in the last session. The previous session we gave example one. This is example two. What the example said: an automatic machine in a manufacturing process is operating properly if the length of an import subcomponent are normally distributed. That means the population is normally distributed, and X is the length of an import subcomponent. With mu, with mean, the population mean equals 117 centimeters, and standard deviation of the population, I mean, which is sigma, standard deviation of the population, is sigma equals 2.1 centimeters. Then we have two questions. The first question: find the probability that one randomly selected unit has a length greater than 120 centimeters. That is easy. That is an introduction to probability, nothing to do with sampling distributions. This part of the question is introduction to probability. Why? That means what is the probability of X greater than 120? What's the probability of X greater than 120? And that's it. This problem we used to solve in introduction to probability. So, in symbols, we say probability that X is greater than 120, and to be able to calculate this probability, we have to use the Z transformation. So transfer from X to Z, and in order to do that, we have to subtract the mean and divide the result by the standard deviation. So we say probability of X greater than 100 equals the probability of Z greater than 120 minus 117 mu over the standard deviation 2.1, which goes to 1.43, and that we can use we can use any table for probability, normal probability distribution, to calculate the probability. From the normal probability table, we get this result. So we have this probability equals this part from 117 to the end, right? Here we get from 1.43. Where is 1.43 here? greater than 1.43, which is the right hand side here, this one. But the table, the normal probability table, gives you this part, right? This part, not this part. Both parts, this and this one, are equal half. Then this one will be half minus this part. Half this one, this part, the right hand side equals half 0.5 minus the value which we get from the table between this part and this part, which will be from 0 to 1.43. The probability of x or z between 0 to 1.43 can be obtained from the table easily, which is 0.236. That's from the normal probability table. So the result will be 0.0764, right? That's all. That's the probability which we need. That's the solution of this part, which is we can transfer it to percentage, which will be 7.64%, right? That's the solution of the first part. It is introduction to probability, nothing to deal with sampling distribution. But the second part relates to the sampling distribution. Why? The second part, B, says that find the probability that if 3 units, then this is the sample, are randomly selected. So it is random sample of 3 units. This means n is 3. Their mean length exceeds 120 centimeters. So what's the probability that the sample mean of a sample of the size 3, right, exceed 120 centimeters? So we know that x is normal distributed from the results which we discussed earlier. X bar then is also normal, whatever the size is, no problem. No, there is no condition to have n greater than 30, because x is normal distributed, then x bar is normal distributed, right? So we have expected value for x bar equals mu, which is 117, and standard error is sigma over square root of n, and sigma and n are given 2.1 and 3 respectively. Then standard error of x bar equals 1.212. Then we can calculate the probability of x bar is greater than 120. The same idea, then the same solution like the previous part. So we transfer it like the solution of the previous part of the question. So the probability that x bar exceeds 120 equals the probability that z is greater than 2.47. Well, that came from 120 minus 117 over 1.212, right? And we can get from the normal probability table this part, which is greater than 2.4, which is this part. This is 2.47, this part. So the same, the normal probability table gives us only this part, and this one are 0.5 half. So the part which we need, the area under the curve here, is equal half the half area under the curve, half minus this part which is probability of z between 0 and 2.47, which from the normal probability table equals 0.4931. So the result is 0.0068, which is 0.68%. Right? That's the solution of the whole equation. Right? Then another example. Imagine we have a large population of, say, invoices with mu equals 252.6 dollars, American dollars, and sigma equals 45.2 American dollars. Mu is the population mean of the whole invoices, the mean of the whole invoices, 200 and 255.6. That's the mean of the population mean of all invoices. And their standard deviation, sigma, equals 45.2, right? Now, if we draw a random sample of size 400, he doesn't mention anything about the sampling, the distribution of the population, but he gave us a large sample, 400, very much greater than 30, very big sample. So the sample size n is 400, and calculate the average value of these invoices, right? What is the probability that it exceeds $260? $260. What is the probability that the sample mean exceeds $260? We have a sample of 400 and invoices. What is the probability of this? The average of this sample exceeds $260. In this example, we are not told whatever the population of invoices is normal, as we mentioned. This doesn't mention anything about the distribution of the population, but he mentioned that the sample is large. So according to central limit theorem, the sampling distribution of X bar is normally distributed. Again, with mean equal the population mean mu, which is $255.6, and standard deviation equals what? Standard or equal sigma over square root of n. Sigma is 45.2 and n equals 400. Then the solution is easy, right? So mu equals to 45.6 and sigma X bar, which is standard or equals sigma over square root of n, which is 45.2 over square root of 40, which is 2.26, right? Then we want the probability that the sample size, the sample mean is greater than 260, and this is P of probability X bar greater than 260 equals, we transfer it to Z, we subtract from 260, 255.6 and divide by 2.26. So we get this. We want probability to be between or greater than 1.5. 1.5 greater than 1.5, which is this part. This part from the normal table, we get this part the area under the curve in this part from 1.59 to the end here, this part. And this part equals half minus this part. The normal probability table gives us only this part from 0 to any point here, which here is 1.595, right? So this is equals half 0.5 minus the value which we get from the table, which is 0.4744, and which is equal 0.0256 or 2.56%. Right? This is the solution of this equation. I hope this is clear. Now, the sampling distribution of the sample mean. And now we will talk about the sample distribution of the proportion. I mean the sample proportion, which is the same idea. If you understood the sampling distribution of the sample mean, you will understand easily the sampling distribution of the sample proportion, which as we mentioned earlier, that you need to know the shape of the curve of the sampling distribution of the proportion, and the other thing is the mean of the distribution and the standard of that distribution. If you know the three things, then you get all. Right? Now, what's the meaning of proportion we are studying? We consider a variable that has only two categories, yes or no, or male or female, the detective or non-defective, defective or non-defective, brand A or not brand B, party A or party B, or whatever. We have some classification here between two categories, right? Categorical variables with two categories only, and we want to calculate the percentage of a category, specific category, right? So we are interested in the percentage of the occurrence of one category, and we call it P. That's the population proportion. In the proportion. So, for example, we have the proportion of males in our population is 0.501, for example, right? Or the population of defective units from a factory is 0.05, right? That's from all products from that factory in general, not a sample, is P. And we want, if we do not know this percentage, and we want to estimate it and make inference about this estimate, we say that we get the sample first, and we have a sampling distribution of the sample proportion, right? So this sample proportion, we call it P hat, here, P hat. This is P, the population proportion, and this is P hat, the sample proportion, right? Then we calculate the sample proportion. We know how to calculate it. It is very easy. If we say we have two categories, and we give each category either 0 or 1, then we have the average itself is equal to the proportion. Or we calculate this, how many yes, and divide it by all, we get the proportions. It's not a problem, right? It's easier to calculate the proportion. Either we give the variable values 0 and 1, and then we have the sum of this variable will be equal to the proportion, right? Or the number of ones equals 10 the same, we get also P hat. In both cases, we get P hat, right? But only this is applied only if we give the variables values 0 and 1. the average equals p hat only in this situation. If we give the variable values, if the variable has values 1 and 2, not 0, 1, then this result or this law doesn't apply. It can be applied only in the case if the variable has two values only, 0 or 1. Then we can consider that p hat equals the average. But if it is not, then we only can use this law. P hat, the sample proportion, equals the number of the characteristics of interest over the whole number of units. How many units have the characteristic of interest divided by the number of units in the sample? Like if we have a sample of 10 students and 8 of them passed the exam and 2 failed, then the rate of or the proportion of people who pass the exam will be 8 over 10 because the sample size is 10 and the number of people who pass the exam is 8. So the sample proportion is 8. But in the whole population, I mean in the whole class, if it is, for example, 50 or 100 or 200, the whole class, we do not know the proportion of people who pass the exam, right? That's the way we calculate the proportion itself, the sample proportion, right? Then we calculate the proportion, right? It is easy here how to calculate it. We have here an example just for calculation of the proportion. We have 10 observations and we have brand A and B. We give brand A the value 1 and B give value 0. So the proportion of brand A unit will be the average, ordinary average, which is 0.6, right? This is the proportion of brand A in the sample. Proportion of brand A in the sample. Or we calculate how many A's. 1, 2, 3, 1, 2, 3, 4, 5, 6 ones divided by the sample size 10. So the other law gives us the same result. 6 over 10, which is 0.6. Right, so if you use this law, it's okay. If you use this law, is okay also. But you can use this law only if the variable itself has only two values, 1 or 0. There is no 2 or 3 or whatever here. Only 1 or 0. If it is 1 and 2 only, two values also. 1 and 2 are two values, but not 1 and 0. Right? You can't use in this case this law. This formula can be only used in the cases where your variable is defined as only 0 and 1 values. Right? Now we calculated the proportion. Then we want to know the sampling distribution. So like the case of the sample mean, the sample proportion, if we have a population like that and we have samples from that population and calculated the sample proportion, we have as many samples, k samples, for example, and each of size n, and we have p1 hat proportion of the first sample to p hat proportion of second sample, p3 hat of proportion of third sample, and k hat is the proportion of the kth sample. And we have kth values of p hat. And these can show us the sampling distribution of the proportion. it will be like that also. So the shape is bell-shaped also and scattered around the original population value P, right? So this shape, the distribution or sampling distribution of P hat. The expected value, which is average, all average, equals, right? And now to be more specific about the sampling distribution of the sample proportion, we will use the binomial distribution as we have a variable of two values, only 0, 1, or 1 or 2, or whatever, as long as it has two values with fixed sample size n, then we have binomial distribution. So the variable x, which has two values only, follows a binomial distribution. So we can use the binomial distribution to estimate the sample, the population proportion P. But P is a continuous variable. So we prefer you to use a continuous distribution, not a binomial distribution. So we will use an approximation of the binomial distribution to the normal distribution. The binomial distribution can easily be approximated to the normal distribution as the sample size is a bit big. How big is it? It's not necessary to be very big, very big. It's only, it has two conditions. Actually, it is one condition, but it's easier to make it two conditions to see if whether we can consider this sample is big or not by multiplying n times p or n times 1 minus p, right? Two things. If we multiply those and we find both of them are greater than 5, then we can consider this sample is big enough to use the normal approximation, right? The normal approximation to the binomial, from binomial to normal. We call it normal approximation, right? As long as the sample size is big with these conditions, then we can safely use the normal approximation. And the sampling distribution of the sample proportion will have the following characteristics. We need three characteristics, like the sampling distribution of the sample mean. Usually three characteristics: mean, standard error, and shape. First one is the mean of the sample proportions, expected value of the sample proportion, which is the population proportion P, right? This is the first thing, right? The mean or expected value of the sample proportions equals the population proportion P, right? The second thing is the standard error of the sample proportions equals square root of P times 1 minus P over N. That's the square root. That means the mean square error or the variance equals this value squared. So we remove the square root. Will become sigma p hat squared equals p times 1 minus p over n, right? Then the third characteristic to define all the sampling distribution of the sample proportion is the shape. The shape will become normal distributed or close to normal or approximately normal, as long as you have NP is greater than 5 and both conditions, both np greater than 5, and n times 1 minus p is greater than 5. So p hat will be approximately normally distributed. So we can use safely the approximation of the normal distribution to p hat. So we can say more specific, the p hat, the sample proportion, has a normal distribution with mean mu p hat equals p, the population the population proportion, and the standard error equals square root of p times 1 minus p over n. That's a complete definition of the sample proportion. Right? Now, example 5 says, from the past experience, 10% of electronic components received from a particular manufacturer are defective. That means the population proportion of defective components, right? 10% are defective. 10% of what? Of electronic components are defective. That's P. If from a particular shipment, not all populations is shipment, like a sample, a random sample of 400 components, even sample from this shipment, not from the whole population. Sample of 400 components only. 400, that's a sample, is selected, and 400 is the sample size, N, is selected. What is the probability that the proportion of defective parts in the sample are between 10% and 11%? So what is the probability of P hat, the sample proportion here, the sample, the proportion from 400 components, P hat is between 10%, 0.10 and 0.11, right? Which is, can be written like that. We have, first of all, we have to see whether 400 is big or not. We multiply 400 by 1%, which is 10%, which is equal 40, and by 90%, 0.9, which is 1 minus 0.1, which is 360. So it is big, both greater than 5, very much greater than 5. So we can use the normal approximation easily. And we have P equals 0.1, 10%, 0.1, right? And standard error equals standard errors, which is sigma P hat equals 0.1 times 1 minus 0.1, which is Q, sometimes we call it. 1 minus P is a Q, right? Which is 9.9, 90%. So standard error sigma P hat, the standard error sigma P hat equals square root of P 0.1 times 1 minus P, which is Q, or 1 minus P, which is 0.9 over 400. So the square, so the standard error of P hat equals 0.05, 0.015. And then we need, from the question, we need what's the probability of the sample proportion P hat lies between 0.010 and 0.11, 0.10 and 0.11. So to calculate this probability, this P hat is normally distributed. We want to transform it to Z. So by subtracting the P, which is 0.1, and dividing by standard error which is 0.015. So it will be like that. Z will be 0.011 minus 0.1 over 0.015. So that means what's the probability of p hat lies between 0.10 and 0.11 equals will be equals according to the normal table between this area 1 1 and 1 2 1 0 and 1 1 which will be from the table 0.2486. So this is the probability which we get from the normal table, right? End of the question. So the last question, the last exercise here, or the last example here, example 6. The truth proportion of voters who support party A is P equals 0.4. What is the probability that a sample of size 200 in here, 200 equals or yields a sample proportion between 0.40 and 0.45, right? So we have all what we need here. Sample proportion and n is large enough. If we mention now in times p and in times p1 minus p, we'll have them all greater than 5. So, and we can calculate the probability. N equals 200. So we want the probability that p hat between 40% and 45% and is large enough to calculate, to approximate this distribution to the normal distribution. And then we have p hat follow the normal distribution with mu p hat equals p, which equals 0.4, and standard error equals the square root of p times p1 minus p over n, which is equal 0.03464, right? And then we can calculate the probability using the normal distribution table. So we can calculate this. Probability of p hat lies between 40% and 45%, and by transforming it to z, we can subtract 40% all sides and divide by 0.03464 all sides. Then we get the required probability, which is probability of z between 0 and 1.44. This part, which can be computed or easily obtained directly from the table, the normal table, and you get it equals 0.4251. This is the required probability, and that's all for the subject, the sampling distribution. And I hope everything is fine for you and you understood everything. Thank you very much, and see you in the next subject. Bye bye.